All right, greetings, classmates. These couple of weeks, we have gone over two things: one, free fall, and two, 2D motion. But today's SI session will cover only 2D only free fall for right now. So to get started, let's get into. Okay, let me introduce free fall really quickly. So free fall basically is one-dimensional motion, but in the y direction. Last time we experienced one-dimensional motion, it was in this way and this way. Right? This is positive x, this is negative x, and that's about it. We had velocities, we added accelerations, and then we had a bunch of kinematic formulas to help with all these calculations. And in the same way, we have free fall, which is going to be motion in the y direction. Now, why does the y direction matter? Why is it different from the 1D motion in the x direction? The reason it is so important is because we have something new to consider, and that is our very, very frequently ubiquitous friend, gravity. Gravity, which affects anything vertically, at least relative to the Earth. So now, not only do you have to worry about velocity, perhaps some acceleration, you also have to worry about a constant acceleration, which is gravity, always pulling you down. And this gravity is going to be equal to 9.8, well, roughly 9.8 meters per second squared. This meters per second squared suggests that it is an acceleration. So you have to consider that every time you're using a kinematic formula. She gave you new formulas, so to speak, but really they are just the old kinematic formulas with A replaced by gravity, with acceleration replaced by gravity. So for example, we have velocity initial squared equals, no, that's velocity final. Velocity final squared is equal to velocity initial squared. Plus 2 times acceleration times distance. And the formula she gave you is going to be this one. And they're basically the same thing, except the new symbols, where this is G. You can do this, but I think it would be better if you understood that this is derived from this, and how it's derived from this. This acceleration is gravity. This acceleration is equal to gravity in this formula. Okay, an important topic that I want to know. Typically, gravity will be negative, but it's not always going to be that way. You would need to understand the kinematic formulas very well in order to understand when gravity will be negative or positive, because these are they're just equations that model the real world. And if you don't understand how the correlation between the equation and the real world, you are going to make mistakes because you lack the context. You lack the understanding of the context. Okay, so let's do this. We're going to start by understanding the formulas. Velocity final squared. The individual kinematic formulas. What's that? Okay, so the kinematic formulas. We'll start with this one, my favorite one. Velocity final squared. Well, you may write it down as velocity squared or velocity naught or whatever. I denote it as velocity final, so I know which velocity I'm talking about, the after velocity. Velocity initial, which is the starting velocity, plus 2 times acceleration times distance. So what does this formula mean? And this is my understanding of it. It may not be true, but my understanding of it is, at least in my experience, it does usually yield correct results. The final velocity this final velocity is equal to an initial velocity plus the velocity it gains by accelerating over some distance. So this thing has some initial velocity and some acceleration. The acceleration is increasing or decreasing the initial velocity depending on what the value of the acceleration is, and this acceleration is affecting us over this distance. This final velocity here is going to be, with respect to this, the difference between the final velocity and initial velocity is going to be the velocity it gained over this distance. So this is equal to the velocity it gained over this distance in this equation. With that said, don't take this as, well, actually, might just be. Anyways, that's how I understand that formula. Second formula I want to go over is going to be the one of the nifty distance formulas, which is distance. And I'm going to write d. Typically, we've written down x, and we might start writing down y, but d I use universally. D is distance. The distance may be vertical, maybe horizontal, might be diagonal. It really doesn't care. So I use d because it's universal. D, some distance is equal to some initial distance. Actually, let me write down the formula first before I start explaining it. Okay, so some final distance, some distance that is covered, right? Some distance that is covered is equal to some initial distance. Say it may be 0, it may be non-zero. This is just the starting point. Is going to be equal to the distance total is going to be the distance that we started with. So it could be here, could be here, plus the distance that we covered due to our initial velocity. So if we add some initial velocity over this time, we will cover this amount of distance, plus the distance that we covered due to increasing velocity. In other words, the distance we covered due to acceleration. So we have this acceleration, and this may affect how the distance we cover even more. For example, if you're in a car and your starting point is 0 and your initial velocity is going to be equal to 10, right? The distance you covered, say in 5 seconds, is going to be equal to 50, well, assuming this is meters per second, this is seconds, we're going to cover 50 meters. However, if you are in this car and you start accelerating, right, you start increasing speed, say you are racing, I'm racing you, of course my car is faster than yours, I have the same initial velocity and my acceleration is going to be non-zero. That means I'm increasing my velocity with every moment in time. You can see why I would cover more distance, because I am increasing my velocity. My velocity is increasing compared to yours. Therefore, I'm going to cover more distance. How much distance? This much distance. This is the amount of distance I will cover compared to you. This is how much more distance I will cover compared to you. With that said, my car is not that fast. In fact, I drive an expensive tricycle on the weekends. So next equation is going to be this the simple increase in velocity formula. So we have final velocity. Again, you might write it as velocity, just velocity. Final velocity is equal to initial velocity plus acceleration times time. And this makes a lot of sense if you break it down. the velocity that we'll end up with is, it correlates heavily with the velocity that we start out with, plus the velocity that we gain due to accelerating over time. And I'll give the same example. This is your car. This is my expensive tricycle. Velocity initial for my expensive tricycle. That's V initial, expensive tricycle. If I am not accelerating, my velocity will stay the same. But if I am accelerating, after some amount of time, my velocity will be greater. So this final velocity will be greater than this initial velocity, given I am accelerating. And that's what this formula means. And I will leave this one she doesn't give you. This is just one I frequently use because I've used it in the past. But I guess I can go ahead and explain this one. The distance that we cover is equal to 1/2 our initial velocity plus our final velocity, all that multiplied by time. So what does this mean? This right here is basically average velocity. So this right here, we'll call it velocity average. If you use a graph, and you note velocity versus time, and you have this right here, right? Our initial velocity is 0, our final velocity is this, and this is the amount of time that we covered. You'll be surprised to learn that this area right here is going to be equal to the distance that we covered. If you've taken calculus or anything like that, you'll know why. But just take my word for it. This area underneath here is going to be equal to the distance we cover by between these velocities and over this time. And you can see why we multiply by 1/2. If you multiply this side, right? If you multiply this right here, this difference right here is going to be, actually, let me take that back. My brain is slowing down. Calm down. Okay. All right, so with all those equations covered, let's move on to the next bit, which is going to be problem 2 of homework, the first homework of Freefall. Okay. So let's read the problem. Okay. So number two is going to be this one. That's a little too big. Let's go 26. 26 is a good size. Pause. A basketball referee tosses the ball straight up for the starting tip-off at what velocity in meters per second? Velocity in meters per second must a basketball player leave the ground to rise 1.05 meters above the floor in attempt to get the ball. So this is our problem right here. If you're wondering why I was typing so fast, it is because my day job, I type angry responses on Twitter to random people I do not like. Okay, so let's say let's what I like to do is I like to draw the problem out first. So a basketball referee tosses the ball straight up for the starting tip off. Let's see. This ball is being tossed up. At what velocity in meters per second must a basketball player leave the ground to rise 1.05 meters above the floor? So we have a basketball player, and we need them to jump up with some velocity that they'll get this high off the floor, which is 1.05 meters above the floor. So this basketball does not factor into our considerations very much. Does not factor into that at all. So I'll just remove that for the sake of this. So let's see, how do we do this? If you're just reading this, and what I like to do is I like to write down my formulas, my kinematic formulas, to see what we have. Velocity final squared is equal to velocity initial squared plus 2 times acceleration times distance. Some distance is equal to our initial distance plus our initial velocity times time, which is the distance we covered due to our initial velocity, plus 1/2 acceleration times time squared, which is the distance we covered due to accelerating over some time. And then we also have velocity final. Velocity final is equal to our velocity initial plus acceleration times time, which is, yeah. Okay, so let's see what we have. We have our initial velocity, which we do not know. So no, we don't have our initial velocity. We have the distance the person is to cover. Do we have anything else? Well, this is free fall, so of course we have something. And if you think about it, no, that is incorrect. That is, it will be gravity. Acceleration is gravity. You might have gotten it right, but I just wanted to tell you got it wrong. So we have the acceleration, which is gravity, which will denote as negative 9.8 meters per second squared. Whether it's negative or positive in these equations, of course, as I said, it depends on the context. If it makes sense in the equation for it to be negative, then it should be negative. But most of the time it is negative. Okay, so we have acceleration, we have the distance we are covering, but we don't have initial velocity. Do we have anything else? Let's see. Okay, let's see. So we don't have velocity initial. We have acceleration, we have the distance we want to cover. We have neither final velocity or initial velocity. We have our initial distance, which is going to be 0 because we're starting on the ground, and then we're going up. Our initial velocity, we do not have. All right, so we have we don't have initial velocity. Do we have the time? We don't have time. We have the acceleration. Too many missing variables here. We have our initial velocity, no. Final velocity, no. Acceleration, we have time. We don't have time. So we're missing a lot of variables to use any of our kinematic equations. And this is typically where you start looking for one of these additional variables. So let's see if can we find initial velocity? Probably not, considering that is what we're looking for. That'll likely be the last thing we find. Can we find the final velocity? Initially, your mind might say no, but if you know, then you'll know that you do have the final velocity. And the reason, if you don't understand, I'll go ahead and explain it down here. moment, please. Okay, so let's say we toss a ball up in the air, right? We toss this ball up in the air. It has some initial velocity. How high does it get off the ground at the very top? And one thing you need to note is that when it gets to the very top, something special happens. It stops moving. Its velocity is 0 at the very top. Its final velocity at the top is equal to 0. And the reason for it makes a lot of sense if you throw an object in the air. If it wasn't 0, it would keep going up because its velocity is not 0, keep going up. Due to gravity, if this velocity is positive, right? If this velocity is positive, gravity will keep on accelerating it, will keep on decelerating it because it is negative compared to the our initial velocity, and it'll keep on decreasing it over time, and eventually we'll get to 0. So this is our initial velocity right here over time, and due to gravity, it will keep on decreasing and decreasing until we get to 0. At 0, will this ball go any higher than this? And the answer is, unless there's a gust of wind coming from the ground, no, it's not going to get any higher than this. It's going to fall down right after that. So, in other words, what I'm saying is, in free fall, at least here, we know what the final velocity is going to be at the very top, because at the very top, it is no longer able to get higher. In other words, its velocity is 0. Its final velocity at the very top is going to be equal to 0. Very cool. Okay, so now you just keep on remembering this, because this will be a motif, will be a reoccurring theme that you will see in a lot of these problems. Okay, so now we know final velocity. Let's see what that changes. So we have final velocity. This one we cannot use because we still don't know initial velocity, and we don't know how long it's going to be in the air. This is a mess. We don't have initial velocity. We don't have the time. We don't have the distance in which it's going to. Actually, we do. We have the distance in which it's going to cover as well, but we don't have initial velocity and we don't have time. This one, we have final velocity, we have initial velocity, we have acceleration, and we have the distance it's going to cover. So this is going to be perfect for finding our initial velocity. And from here, we just plug and play. Let's manipulate so we are able to find the final, the initial velocity. So velocity final squared minus 2 times acceleration times distance equals velocity initial. This is just some algebraic manipulation. I subtracted 2 times acceleration distance for both sides, getting rid of this side. Hopefully you understand. If you don't, do review that. You will definitely need it. Review algebraic manipulation. You'll need it to find certain variables a lot. And then we square root it in order to get rid of this right here, and we have the velocity initial. So let's plug in our values. Our velocity final is going to be 0 squared. Our velocity final is going to be 0, and then we square it, minus 2 times the acceleration, which is going to be negative 9.8 meters per second squared, times distance, which is going to be 1.05. And this is where, okay, no, this makes sense, because this is the distance that is covered while accelerating or decelerating in our case. This is the distance that is covered while we're decelerating. Okay, so this is going to be equal to it's going to be equal to 4.5365 and so on What are the units? Velocity, which is meters per second. This is going to be our answer right here. And does this make sense? Well, if the velocity was negative, the fool will go straight into the ground. They won't get that high. They won't get high at all. So they won't. It won't make a lot of sense. This seems somewhat reasonable. So let's suggest that that is the answer. All right, next question. Okay, free fall number 5. Number 5, which is a bit of a lengthy question. It has 2 parts. Standing at the base of one of the cliffs of Mount Arapiles in Victoria, someone in Australia. Someone from Victoria, Australia is gonna come and kill me because of the way I pronounced Arapiles. That's okay. If I disappear, you know why. A hiker hears a rock break loose from a height of 120 meters. He can't see the rock right away, but then does. 1.51 seconds later. Part A asks, how far in meters above the hiker is the rock when he can see it? And B, how much time in seconds does he have to move before the rock hits his head? I'm hoping this feller survived. Well, let's find out. We'll see. We'll see if he has a reasonable amount of time to react. Okay, so standing at the hiker here's rock break loose, 1.120. He can't see the rock right away, but he does 1.5 seconds later. How far above the hiker is the rock when he can see it? So he sees it 1.5 seconds later. So the rock is initially stationary, and this rock, let's say for the sake of this problem, it's 120 meters above this guy's head, this feller's head. Yeah, it's a big feller. And he can't see it until about 1.51 seconds later. So this is t equals 0, and at t equals 1.51 seconds, it has fallen some distance. Distance fallen. I'm gonna just name it change in distance. It's unknown. And this is the moment where the guy looks up and sees the rock. So how far above in meters is the rock when he can see it? If we look at this, we can see what distance above the guy it is. It's going to be this 120 meters minus whatever distance it covered while the guy wasn't looking. So in order to find this, we need to find this. So let's start with writing our kinematic formulas. Okay, so let's underline what we have. Do we have initial velocity? Let's see, let's think. This rock breaks off and then starts falling. Initially it was stationary, and then the mountain let go of it, so to speak. So initially it was stationary, and then the mountain let go of it, and now it's falling. So we do have our initial velocity, which is going to be 0 meters per second in this case. Do we have acceleration? Acceleration, in this case, the only acceleration that we can see here is, that's right, gravity. Hopefully you said gravity. It's going to be negative 9.8 meters per second squared. 0 meters. And let's see, do we have D? We do have D, but what does that mean in this context? Our final velocity is equal to our initial velocity plus the velocity that it gains over some distance. We're not looking for the velocity here. We're not looking for the final velocity here. The final velocity here. So we really don't have D in this case. D is what we're looking for. So we don't know final velocity. We know initial velocity. We know acceleration. We know distance. We know time as well, which is going to be 1.51 seconds, which is the time it takes before the guy recognizes the rock is about to kill him. So with all this, we also have the initial distance, which is not going to be 120. In this case, well, with respect to where it's falling, this is the initial, this is the final. The initial in this case is going to be equal to 0. Why didn't we use this distance? As I said, it doesn't make sense in context of this problem. Well, it might, but I'm gonna just say it doesn't, because yeah. Okay, so 0 meters. Okay, so let's underline what we have. We have time, we have our initial distance, we have acceleration, and we have initial velocity. We have initial velocity, acceleration. We don't have the distance it covers in order to reach this final velocity, and we don't have this final velocity. So let's move on. We have initial distance, we have our initial velocity, we have the time, we have the acceleration, and we have the time. We don't even need to look at this last one. We are able to find the distance it covers with respect the distance it covers from the point that it starts falling with its initial velocity, and the distance it covers due to acceleration over time, which is this equation right here. So let's go ahead and find out what that distance is. So this distance is going to be, change in D, it's going to be equal to, let me delete this actually. I don't know what to delete. Okay, our change in distance is going to be equal to our initial distance, which is going to be 0 meters, plus our initial velocity, which is 0 meters per second, times time, 1.51 seconds, plus 1/2 the acceleration, which is negative 9.8 meters per second squared, times time, times our time, 1.51 seconds. And remember when I said it does depend on the context whether or not gravity can be written as negative. Does it make sense? Well, the distance it is falling is going to be negative compared to where it first started falling. This right here, and then all of a sudden its elevation decreases. So it does make sense for the distance it covers due to acceleration over time to be negative. It does make a lot of sense. So it will be negative in this context. So this will be 0, and then we just need to use our handy calculators for this last part. Divide by 2. Oh, this is squared. Times 1.51 squared. So change in distance is equal to 11.17249 meters. Whoo, okay. Okay, so that's the first part. So we have some new information. We have the answer for this first part. Yeah. Of course, sig figs will probably may be important. I'm not exactly sure. I still don't have access to Cengage just yet. So I'm hoping this is right. I'm confident it's right, but I can't promise. So okay. How much time in seconds does he have to move before the rock hits his head? Okay, so let's redraw what we have here. The guy, the bloke, the gentleman, which is some new distance. Oh! Timeout. We didn't finish this first part. How far meters above the hiker? We've only found the distance that it falls. We need to find the distance above its head before we need to find the distance above his head, which is going to be this distance minus 120 minus the distance we found, which is going to be 108.82751 meters. This is going to be our answer. I'm going to take this and save it over here. Oh, okay. I'm gonna just put this here. Okay. So now, how much time does he have before? In seconds does he have before the rock hits his head? We have this distance now, which is going to be the distance above his head that the rock is, which is going to be 108. Oh, it's going to be this value right here. I'm just going to steal this. Thank you. Mom said it's my fault. It's my fault. Okay, so we have the distance. We have the distance the rock is above the guy's head. Just going to be this distance. Do we know the velocity at this point? We don't know the initial velocity at this point. We know the acceleration, which is equal to gravity, which is going to be equal to negative 9.8 meters per second squared. Is there anything else? We don't know its final velocity. What's acceleration? We don't know how much time it's going to take before it hits the ground, because that's what we're looking for. Okay, let's see. Let's go ahead and write down our kinematic equations again, see what we have. Okay, let's underline what we have. We don't know the initial velocity. We know the acceleration. We know the distance it'll cover before this final velocity is hit, but we don't know the final velocity. We know the initial distance, which at least in this perspective, it might be 0. Well, actually, it really depends on how you write these numbers. If you write these velocities negative as well as the acceleration, you could find how much the distance decreases. So if you want, you can write this as this, or you can write it as 0, just to make sure you understand the context in which you are writing it. So we have the initial distance, which could be this or 0. We have the initial velocity. No, we don't. We don't have the initial velocity. Do we have the time? No, we don't. We have the acceleration. We have the distance. it will cover after? Yes, we do. It's either 0 or this. Do we have the final velocity? No. Initial velocity? No. Acceleration? Yes. Time? No. So this last one is basically dead useless. We have too many variables here. This one, we could either find final velocity, initial velocity, or time, initial velocity or time, initial velocity or final velocity. Let's pick one that we can possibly find. I will eliminate final velocity because in order to find final velocity, you will definitely need the initial velocity. So final velocity is out of here. We're not going to look for that. Initial velocity, we could find. Time is going to be the last thing we find. That's a dead giveaway based out of this question. So we'll go ahead and look for the initial velocity and see if we can find it. So the initial velocity here is unknown. But remember, we have more context. The rock did fall some distance from a standstill. So we've calculated, so we found similar, we've gone through similar problems before in the past where we found the velocity that an object has after accelerating over some distance, which is going to be this kinematic formula right here. So we can use this formula right here to, with this data, to find the final velocity. Well, in this case, it's going to be initial velocity, final velocity. This final velocity is going to be our initial velocity in this case, because we are looking from the point after it's fallen some distance, which is now our initial velocity. Ooh. Okay, so let's go ahead and look for that. All right, so our velocity final squared. Do we have our initial velocity? The initial velocity in this case is going to be 0 squared plus 2 times the acceleration, which is negative 9.8 meters per second squared, over the distance that it falls. So the final velocity after it's fallen some distance is going to be equal to its initial velocity squared plus 2 times the plus the velocity it gains over falling some distance or accelerating over some distance. And that distance will be, where's the distance? It's going to be equal to 11.17249 meters. It's going to be equal to that. So let's go ahead and put that in our calculators. Velocity final squared is equal to 21898. This is 21898 meters per second squared. This is not what we're looking for. We're going to look for the square root of this, which is going to be equal to 14.798 meters. Okay. So our final velocity, after the rock has fallen some distance is going to be equal to this. I'm going to put this here so we're not confused as to, oh, where are we? I'm going to put this here so we're not confused. We don't get our data confused. So the velocity that it has after what is it called? Okay, so the velocity it has after it falls some distance is going to be equal to this. And that is going to be our initial velocity over here. Because we are starting, because our initial point is going to be our final point over here. Okay, so we now have the initial velocity, which is, we can underline new stuff. initial velocity, initial velocity, initial velocity. And we're looking for how much time he has. So we're looking for time. We can't use this one because we still don't know the final velocity. We could possibly use this one, but I'm gonna tell you right now, you don't want to use this one, and that is because the algebraic manipulation is disgusting. So we have d minus di is equal to vit plus 1/2 at squared, and that then becomes d minus di, so I'll just change this to change in d, is equal to t times the velocity initial plus 1/2 acceleration times time. And now you have some goofy looking algebra 2 equation that I really don't want to deal with. So let's see if we can find even more variables. Can we find any more data? So if we look at this one up here, though we cannot find time, we can find the final velocity that this rock has after it's fallen this distance. So let's go ahead and find that. So the final velocity squared is going to be equal to, and the reason I'm going after final velocity is you really want to get as much data as possible so you can use as many of these equations as possible. So there isn't, it's not just because I feel like it. Well, yes, it is because I feel like it, because I don't want to deal with this one, but also because I want to be able to have more assets, so to speak, so more resources to use. Okay, so final velocity squared is equal to the initial velocity squared. In this case, the initial velocity is going to be this one, which we've written down right here. This one's no longer unknown, which is right here. This is our initial velocity. So 14.798 squared plus 2 times acceleration 9.8 meters per second squared times distance, the distance it falls, which is 108.82751. And before we multiply this out, let's make sure this makes sense. The final velocity that it has is equal to the initial velocity it has plus the velocity it gains over the distance it accelerates. And it is accelerating in the same direction as this. It is accelerating in the same direction as its initial velocity. So this right here is going to add to our initial velocity. And it's a good thing I did that, because if you didn't, you would get that this value is negative 2133.019 and some more numbers, which will subtract from this one. And that really doesn't make any sense. Why would its velocity, right? Why would its initial velocity and its acceleration is in the same direction? So its final velocity is going to have a greater magnitude than its initial velocity. But this equation, if we're not careful, is going to take away from our initial velocity. It's going to take away from our initial velocity, which will result in a smaller final velocity than we started out with, which doesn't make a lot of sense. So this in our case is going to be positive. Gravity is going to be positive. This is in the same direction as our velocity, which is why you need to be careful. You absolutely need to be careful. You have to consider the context in which these things are happening. You can't just plug and play and expect all the numbers to be right. Because in this case, if we did, the numbers would be very wrong. So the answer I gotten, when we add these two, final velocity is going to be equal to 48.7 3.4974 meters per second. This is going to be our final velocity right here. Okay, so now we have final velocity. We can underline some new stuff. And with that, we have access to time right here quite easily. We don't need to use you no more. Goodbye. So 48.4974 minus our initial velocity. Well, let me manipulate this first so you don't get confused. Initial velocity divided by our acceleration is equal to the time. So our final velocity, which is this, our initial velocity, which is 14.798, divided by the time, no, not the time, divided by the acceleration, which is negative 9.8 meters per second squared. And you also need to consider whether or not this is going to be negative or positive, because if we plug this in the way it is right now, we will get negative 3.4387 seconds. So in other words, this rock will take negative 3.4387 seconds to reach this guy's head, which doesn't make any sense considering this guy's name is probably not Tenet. So this gravity is going to be, in this context, it will be positive, or you can just take the absolute value of it. It just make sure when you're plugging in stuff, it makes sense. Your answers make sense, that your values make sense. So, in other words, after all that, the final velocity, the time that he has before the rock removes him from this planet is 3.4387 seconds. My apologies, I'm getting a little tired. Woo! Okay, that was a hefty problem. Okay, let's see. Do we have any other problems we can go over? You know what? I think that will be the end of our session for today. Hopefully you understood everything I went over. If you're watching this considering nobody's here, that's okay. It's absolutely fine. No one needs to attend these sessions. Just make sure you send me material to work with. These questions were sent from a student in our class. So I'm working on the question, and hopefully me breaking it down will help you understand how to approach these questions. So if you have any problems, please DM me on GroupMe. If you have any questions, DM me on GroupMe. Yeah, and that'll be it.